This video lesson has been recorded for students of Triple Science in Year 10. So that is the class being taught by Miss Hawkins and Miss Evans. My name is Mr. Crozier. I am going to be recording some videos for Triple Science content, and that is to go alongside the trilogy content that Miss Hawkins is setting you via Show My Homework. So I'm going to be introducing you to Structure and Bonding Topic 2. Right, why do we study structure and bonding? Scientists study the structure of atoms and bonds so we can understand and improve the properties of materials and chemicals. Now, you have already studied a fair amount of this as part of the trilogy course. You have looked at ionic bonding and structure, and covalent bonding and metallic bonding, and also how the structures lead to those chemicals having certain properties. We'll try and get in a bit of revision of that as we go through the topic, but this is going to be new content, new structure and bonding content that you haven't come across before. Although we're going to start with the patterns in the periodic table. So hopefully a lot of this will be familiar to you, and really this is to try and get some overlap between the trilogy and the triple content. Most of the stuff in this topic will be new to you. Right, so the driving question, what are the patterns of the periodic table? This is mostly revision, but there might be some new bits and pieces in here as well. Okay, so periodic table, which you are very familiar with, and one of the things we need to consider with structure and bonding is that the structure of a chemical causes its properties, but the structure it takes is dependent on the number of electrons in the outer orbit, and therefore what type of bonds will be formed by that particular atom. So we need to revise electron configuration. Hopefully this will be really straightforward for you. In class, I would get my students to work out the electron configuration of all these different elements and then start looking for patterns. So feel free to pause the video for a moment, do 3 or 4 examples just to check that you understand electron configuration, and then we'll go through it. So pause the video now. Okay, let's start looking at the electron configuration. Just in case you've forgotten how to do this, we look at the atomic number of the atom. So for example, lithium, you do need a periodic table for this, so you can keep referring to the earlier slide in the video. And the atomic number, remember, is the smaller of the two numbers. So 3 in the case of lithium, 7 is the mass number. So 3 electrons, and then 2 electrons will go into the first orbit, sometimes called a shell, sometimes called an energy level, and that means the third electron will go into the next orbit. So we get an electron configuration or electron structure of 2, 1. And hopefully this is familiar and straightforward for you. Right, now if we do that for the other elements that I showed, beryllium, for example, has an atomic number of 4. Therefore, there will be an electron configuration of 2, 2. Okay, so this should be really easy for you, hopefully, if you remember your trilogy content. So quick check, what is the definition for electron configuration? Pause the video and decide whether it is A, B, C, or D. Okay, let's move on, and the correct answer was D, the pattern of how many electrons are in each energy level, or shell, or orbit. So the maximum for the first 3 orbits is 2, 8, 8. Right, so far, so straightforward. Let's look for some patterns. If I fill in all the electron configurations for these elements, we need to look for the patterns that we can see. Right, you may well have come across this before. In group 1, all of the elements have 1 electron inner outer orbit. In group 2, they all have 2 inner outer orbit. So there's a clear pattern there that the group number also tells us the number of electrons in the outer orbit. Now, a group is a column. The reason why elements are in groups is because they share the same properties, the same sort of reactions, the same sort of physical properties. But they share the same properties because they have the same number of electrons in their outer orbit. There is also a pattern going across the rows of the periodic table. The rows are called periods, and we get varying properties across the rows of the periodic table. But if you have a look, period 1, there's only 1 orbit of electrons which has electrons in it. Period 2, there are 2 orbits of electrons. Period 3 has 3 orbits of electrons. Period 4 has 4 orbits of electrons. So with each row of the periodic table, we are starting a new shell of electrons. So period 3 has 3 shells of electrons. So if you know the period number and group number of an element, it is really quick to work out what it would be. Period 3, there must be 3 electron shells, and if it's a group of 4, the third of those must have 4 electrons. Okay, right, moving on. Quick, because this is revision. So the columns of the periodic table are called groups. They share the same chemical and physical properties, and they have the same number of electrons in the outer orbit. And you need to be familiar with groups 1, 2, 3, 4, 5, 6, 7, and 0. The noble gases over there. And then the rows are called periods. Sometimes people forget that hydrogen and helium counts as a period 1. So period 2 starts with lithium. Okay. And elements in the same period have the same number of electron shells. Right, now reactivity, there's a pattern of reactivity of the metals. Metals are found on the left of the periodic table, and they get more reactive towards the bottom left-hand corner. Hopefully you are familiar with group 1, getting more reactive as we go down the periodic table. You also get more reactive from right to left. All right, explaining the properties of group 1 elements. I'm just going to mute this so that I can talk over the top of it. And we should be able to see the alkali metals from group 1. Again, this is revision of trilogy content, but always a good idea to keep revisiting early material. Right, so we're going to explain why they get more reactive down the group with reference to their electron structure. Hopefully you have seen their reactions before. When they are placed in water, they fizz. They are physically soft to cut. They also get physically softer down the group. The metallic structure and bonding gets weaker down the group, so they are softer to cut, and they get more reactive down the group. So they will fizz more. So lithium floats and fizzes a little bit. Hydrogen gas being produced, lithium hydroxide being produced in the water. And then you can use indicator to show that alkali is being produced, which is why they're called alkali metals. Lithium hydroxide is produced, sodium hydroxide is produced, potassium hydroxide is produced. And then obviously sodium reacts more, a more vigorous reaction. And then potassium is the one with the purple sparks and the flames, reacts the most out of those 3. If we were to move further down the group, rubidium and cesium would be more reactive again. So hopefully that just reminds you about this. They get softer down the group, they get more reactive down the group. But the question we need to answer is why, and we need to use electron configuration for that. Just to point out that reactivity is a chemical property, softness or hardness is a physical property. Right, so firstly, they have similar properties. So they all react with water. They're all relatively soft for a metal because they're in the same group. We place them in the same group because they have similar properties. They all have 1 electron in their outer orbit, 2, 1, 2, 8, 1, 2, 8, 8, 1. But why do they get more reactive down the group? Right, well, when they react, they lose their outer electron. They have 1 electron in their outer orbit, and they lose it when they react. And if you notice that because there are 3 electrons with negative charges, there will also be 3 protons with positive charges. When it loses an electron, the protons remain in the atom, so it's lost a negative. It therefore has 3 positives, but only 2 negatives after it has reacted. So when they react, they lose their outer electron. Okay, but the atom would quite like to be able to attract that electron back in again because positives and negatives do attract to each other. So it's not always easy to remove an electron because it is attracted to the nucleus. Right, but you know, they are pretty reactive, so they do lose their outer electrons relatively easily, but it's not always as easy as it should be. Right, lithium is less reactive than the others because its outer orbit is closer to the nucleus, so its outer electron is more attracted to the nucleus, therefore it's more difficult to lose that outer electron. Moving down the group then, the outer electron gets further from the nucleus, therefore it is easier to lose the outer electron, making it more reactive. Okay, so the smaller the atom, the more tightly it keeps its outer electrons. It's closer to the nucleus, it's more attracted to the positive protons. As you move down the group, the atoms become bigger, the outer electron is further from the nucleus, therefore is more easily lost. Okay, so the larger the atom, the weaker the attraction between the nucleus and the outer electron, the easier it is to lose that outer electron. Okay, time to put this in your own words. If there's somebody in the house, then I suggest you say it out loud to them. And if there's nobody there, maybe just speak to yourself, talk to yourself. You might feel like a bit of a weirdo, but it's okay. Putting it into your own words is a really good way to tell if you understand it. There's going to be a writing task later on where you're going to write it down properly. So you don't need to write it down now. Just try and do it verbally. Okay, pause the video and come up with your own answer. Why do they get more reactive down the group? Pause it now. Okay, here we go with the answers. I hope you did think of your own way of putting this into words. Here's what I said. The alkali metals are all in group 1, so they have one electron in their outer shell. When they react, they lose the outer electron. That forms a positive 1+ ion. Down the group, the atoms get larger. The outer electron is further from the nucleus, less attracted less strongly to the nucleus, so it's easier to lose the outer electron when the atom is bigger. Right, okay, how does that compare to group 7? Right, again, let's just mute. Is that muted? Oh, yes, it is. Right. Now, group 7 are the halogens, fluorine, chlorine, bromine, and iodine. They are non-metals. Fluorine is a colorless gas, chlorine a yellow-green gas, bromine an orange liquid, iodine a purple solid. But they're all non-metals, and they are all able to react with metal. So this is some iron wool in a test tube, and the iodine, purple vapor, is going to be warmed. That's why it's turned into a vapor, and it is then going to react with the metal to form a salt. So when group 7 reacts with metal, it forms a salt. Okay. Now, if you try different group 7 metals, what you find is that they get less reactive down the group. So here they're actually working their way up the group. This is bromine next, orange liquid, and you can see it reacts more vigorously with the metal. If you move up the group again to chlorine, then we should see that it's more reactive again. Chlorine is pretty toxic and dangerous to use. That's why they're doing it within this equipment. But when they eventually get it reacting, there's the chlorine gas being generated. The chlorine gas then moves into this tube, warm it to get the reaction going, and you can see it's much more vigorous reaction, much faster. Chlorine is more reactive than bromine, which is more reactive than iodine. So they get more reactive up the group. In other words, less reactive down the group. They're in the same group because they have similar chemical and physical properties, because they all have 7 in the outer orbit. Okay, and yet they get less reactive down the group. So we need to look at why that is. Why is it the opposite way around to the alkali metals? Well, when group 7 elements react, they gain an electron. 7 in the outer orbit, they need to gain 1 to complete that outer orbit. Okay, when they do that, they are gaining a negative, so it becomes a negative ion. Gains 1 electron, so 1 minus. Right? Now, when the atom is small, the outer orbit is closer to the nucleus, so it's easier to attract in that electron. With a larger atom, the outer orbit is further from the nucleus, so it's more difficult to attract in that electron. Remember, the nucleus contains positive protons, which is normally good at attracting electrons, but if the outer orbit is far from the nucleus, it's more difficult to attract in that electron. So the bigger the atom, the harder it is to attract in an extra electron. So therefore, as you go down the group, the atoms get larger, it becomes more difficult to attract an electron to complete the outer orbit. Okay, so the smaller the atom, the more easily it attracts an electron, and the bigger the atom, the more difficult it is to gain an extra outer electron. So they are getting less reactive down the group, the opposite pattern to the alkali metals, because they are gaining an electron rather than losing an electron. So it all works the opposite way around. The smaller the atom in group 7, the stronger the attraction between the nucleus and the outer electrons, the easier it is to gain an electron. So comparing the two groups, in group 1 they are metals, they lose an electron from the outer shell, it gets more reactive down the group. But in group 7, they are non-metals, they gain an electron to the outer orbit, it gets less reactive down the group. They are the opposite to each other. Right, time to put it in your own words. Think it to yourself, say it out loud, tell somebody else if there's somebody in the room. Why do the halogens get less reactive down the group? Pause the video and put it in your own words now. Okay, let's have a look at what I said for my answer. The halogens are in group 7. They have 7 in their outer shell. When the halogens, that should say, react, they gain an electron, forming a 1- ion. Down a group, the atoms get larger, the outer orbit is further from the nucleus, so the outer electrons are attracted less strongly. It's more difficult to gain an electron to the outer shell when the atoms are larger, further down the group. Okay, comparing it to group 0. Right, group 0 are the noble gases: helium, neon, argon, krypton, xenon, radon. Okay, so group 7 on the right-hand side of the periodic table there. And let's have a look. Why is it called group 0 rather than group 8? Well, group 8 doesn't work for helium because it only has 2. So if we called it group 8, helium wouldn't match the pattern. But if you think about the next orbit, has 0 on it. That is true for all the atoms in that group. Okay, so 2, 2, 8, 2, 8, 8, it would be followed by 0 in the next orbit. So if we call it group 0, then all of the atoms fit that pattern. We don't normally write the 0 down though. Now, because they've got a complete outer orbit of electrons, that means they don't lose electrons, they don't gain electrons, they are unreactive. Okay, so they are unreactive because they do not lose or gain electrons. It's also why they're all gases. They don't form bonds, so the atoms float around separately to each other without bonding because they can't lose, they can't gain, they can't share because they've already got complete outer orbits. Right, hinge question time. Pause the video and decide which of these answers is true. Is it A, B, C, or D? Pause it now. Here we go with the answer. The answer is C. Alkali metals get more reactive down group 1. Halogens get less reactive down group 7. Noble gases are always unreactive and in group 0. Okay, it's time for the writing task of this lesson. Now, what you need to do is put the driving question at the top of your page or at the top of a Word document and underline it. Then you're going to work your way through orange, green, yellow, and blue. Remember, orange means describe the facts and key words. Explain means explain the main idea of the lesson. Yellow means use your understanding to explain a situation in more detail. And blue means combine together difficult ideas to further extend your explanations. Here are some sentence starters. So this will help you to lay out your work. Make sure you write in full sentences. Don't do one-word answers because then you'll be able to, if you write in full sentences, you'll be able to revise it afterwards. So pause the video on this slide and use the sentence starters to help you work your way through. Put the driving question first, work your way through orange, green, yellow, blue, writing in full sentences. Take as long as you need, probably 10 to 15 minutes. And then when you're ready, you can play the video again to find the answers and mark your work. But don't look at the answers until you've done your writing. Okay, year 10, pause the video and do your writing task now. Okay, I hope you did this properly and put some good effort into your work and actually wrote out your answers, because then you can mark it and see what you got right, what you got wrong. If you just skip straight to the answers, then you're just cheating yourself and you won't learn as much. It's really important to assess yourself to see how much of that you could actually do. And please remember to tick your work if it's correct, and if there was something you missed, write it in. You are allowed to add to your answers. Okay, describe the main facts and keywords of the lesson. How do we work out electron configurations? Use the atomic number to find the number of electrons. Then work out how many in each orbit. 2 in the first shell, then 8, then 8. Right, what does group mean? Group means a column of elements which share the same or similar physical and chemical properties. They also have the same number in their outer orbit, which I think I've written in the green section coming up on the next slide. Period means a row of elements going across the table. The properties vary, but actually the properties will repeat every 8 or 18 elements. That's the point at which we start a new row. Okay, explain. What are the patterns? The pattern between group number and electron structure is if they're in the same group, they have the same number in their outer orbit. For example, in group 1, they all have 1 in their outer orbit. In a period, the period number tells us how many electron orbits or shells will have electrons in them. For example, in period 3, they all have 3 shells of electrons which contain electrons. Okay, yellow, explaining alkali metals. When alkali metals react, they lose their outer electron. The outer electron is negative, attracted to the positive nucleus. At the top of the group, the outer electron is close to the nucleus and therefore more attracted and more difficult to lose that electron. But as you go down the group, the atoms get larger, the outer electron is further from the nucleus, less attracted, therefore more easily lost, which makes potassium more reactive than sodium or lithium. Okay, then blue, comparing that to group 7 and group 0. So in group 7, it's the opposite way around. They gain an electron when they react. The smaller the atom, the more easily it attracts the outer electrons. But as you move down the group, the atoms get bigger, the outer electrons are further from the nucleus, more difficult to attract an electron, therefore it makes them less reactive. So the larger the atom, the harder it is to gain an electron in group 7, so the less reactive it is as you move further down the group. And then comparing that to group 0 have complete outer orbits with 2 or 8. They are unable to lose or gain electrons, which makes them very unreactive. I've put in some extra detail here, just clarifying that in group 1 they lose the outer electron, and by doing so they gain an empty outer orbit, which makes them the same as the noble gases. We call that gaining the noble gas configuration. In group 7 they gain an electron to complete the outer orbit, and by doing so they get a full complete outer shell, sometimes called the noble gas configuration. So group 1 and group 7 can gain the noble gas configuration. In group 1 they lose an electron to do that, whereas in group 7 they gain an electron to do that. Okay, time to decide how successful you were in this lesson, not just in terms of specifically what you could achieve, but what that says about you. Were you able to describe the main facts and keywords of the lesson? Were you able to explain the main idea of the lesson? Could you use that idea to explain the situation in more detail? Could you combine together difficult ideas? So, for example, today I achieved use because I could explain the pattern and reactivity of group 1. Or today I achieved combine because I can compare and explain the reactivity in group 1, group 7, and group 0. And whatever you have managed to achieve today, I suggest you show somebody at home your work, let them know that you've done the lesson and that you've put a good effort into it and done some good detail. And hopefully you can be really pleased with yourself for completing this work as well. This is mostly, in this first lesson, revision of information from trilogy topics. We will be moving on to more unique triple science content in the second and third lessons. But what you need to do now is go back onto Show My Homework. There is a 10-question quiz to complete, which hopefully will be nice and straightforward now you've done this lessons. And a big well done from me, and a big well done from Miss Hawkins and Miss Evans as well for sitting down and completing this work properly with good effort and good detail today. Well done, Year 10. There will be more videos from me on this triple science content coming up very soon. So look out for lesson 2, which is the next lesson, where we'll start to look at transition metals. Okay. Thank you. Have a good day.